Okay, this lecture is on Chapter 8. This is on thermochemistry. And I'm not going to spend a lot of time on the first, couple of sections. They're really definition-based. I will spend most of the time talking about the problems that we do with this type of material. But anyway, just to kind of start us off, we define energy as the capacity to supply heat or do work. There's two basic forms of energy, kinetic energy and potential energy. As described here, kinetic energy is the energy of motion, potential energy is stored energy. One of the first laws tells us that energy cannot be created or destroyed. It can only be converted from one form into another. We'll use this in application to chemical reactions in terms of figuring out the change in enthalpy and other types of quantities. Total energy equals the sum of kinetic energy and potential energy added together. We'll focus a lot on thermal energy. This is the kinetic energy of motion, molecular motion. We measure it by finding the temperature of an object, and the amount of thermal energy that's transferred from one object to another as a result of a temperature difference between the two is what we know of as heat. And that's what we'll be talking about in terms of these reactions. The first law of thermodynamics tells us, again, that we can't create or destroy energy. It can only be converted from one form into another. That means that your total internal energy of an isolated system is constant. That means that you could take the change in energy, that would be the final energy minus the initial, because some of it was lost to the surroundings. A couple things on the notations you see here. Wherever you see that triangle, it means change in. So here it means change in energy, but you're going to see it used in change in enthalpy, free energy change, change in temperature. So that triangle again means change in, and usually that means the final state minus the initial state. So whether you're talking about energy or enthalpy or temperature, you're talking about the difference between the final and initial states. We'll come back to that into and out of the system and surroundings when we talk about in terms of enthalpy changes. So here you can see how we express this in terms of chemical reactions. So this is one way to show the amount of heat energy that's, in this case, released by this process. So you're going to see a few ways that this is shown. One way is to actually write the amount of energy in the chemical equation reaction that you see here. So methane combusting in oxygen, producing carbon dioxide and water, also releases 800 kilojoules of energy. So when it's written on the right-hand side, as you see here, that's to indicate that that energy is given off by the reaction. Alternatively, we could write it on the left-hand side of the arrow with the reactants, and that would indicate the amount of energy that's required by the reaction, or absorbed by the reaction is another way to word that. The change in energy here, if we were to do that, the final minus initial, you'll see that the change in is reflected as minus 802 kilojoules. Again, the sign here is telling you how that energy is either being released or absorbed. So where you see a minus sign in front of a change in energy, and we'll talk about it in terms of heat energy and enthalpy. When you see a negative, that's indicating that's the amount of energy that's given off by the reaction or released by the reaction. If you see a positive sign, or essentially no sign, that means that that's the amount of energy that was required or absorbed by the reaction. And you can see that reflected in the way that it's worded down below. Another thing to note here is this energy that you see here is specific to the reaction shown. So that means that the molar amounts that you see correspond to the amount of energy that you see. So for example, in this case, I'm reacting 1 mole of methane with 2 moles of oxygen, and I release 802 kilojoules of energy. If, for example, I said I had 2 moles of methane and 4 moles of oxygen reacting, and asked you to calculate the amount of energy that was released, you would need to double that 802. Because that 802 is specific to the molar ratios that you see written in the formula. And this will come back as you are asked different problems related to reactions. We define a state function, this is something new here in this chapter, as something whose value depends only on the state or condition that it is in, not on the path it used to arrive at that state. So they give an example here of kind of a map, that your position on the map is a state function, but things that would not be state functions would be any work you expended or money that you spent sort of traveling from one place to another. Those would not be considered state functions. But the position itself is a function because it's only depends on where you are right at that moment, not on the path you used to arrive. Another equation, or sort of first equation shown here, is a definition of work. Work is defined as a force times a distance, and we can use that to calculate pressures of gases, for example. So this is also equivalent to, the work is also equivalent to minus P delta V. You can see that sort of at the bottom. The P is for pressure. The delta is change in volume, so that'd be final volume minus initial volume. And we'll use this a bit when we talk about, when we talk about gases, which I believe is the next chapter. But that's one formula to be familiar with and be able to use. And again, this is just showing that formula. There are a lot of formulas here, none of which are really critical to the problems that we're going to do. They just sort of show the interplay between energy and heat. We're going to focus more on looking at actual equations and calculating heat from those equations. But it's important to point out that the Q that you see here is heat. So where you see the symbol Q, that's referring to heat energy. And we'll often talk about an enthalpy change or a heat of reaction. These are both the same thing. They're symbolized with that delta H. And as I said before, that delta, or the triangle, means final minus initial. So when we're talking about the state function of enthalpy, if we talk about the change in enthalpy, we're talking about the final enthalpy minus the initial. In terms of relating this directly to reactions, this is reflected in the enthalpies of the products minus the sum of the enthalpies of the reactants. And you'll see this come into play when we do several problems regarding enthalpy. I'm going to skip this, but talk just a little bit about what we mean by heat capacity. I know that you're doing a calorimetry experiment in the lab, so we won't really focus on the application piece here. But you should be able to do these types of calculations. So I would have all three of these formulas written on your exam sheet. So the first is heat capacity. Heat capacity is symbolized by the capital C. It's the amount of heat that's required to raise the temperature of an object or substance a given amount. And the equation that's used here is Q, heat, is equal to the heat capacity, C, multiplied by the change in temperature. Again, that would be final minus initial temperature. The second type of calculation reflects the definition of what we know as molar heat capacity. So that's capital C with a lowercase m. This is defined as the amount of heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius. So this is just a more specific definition, and you should be able to do calculations involving this. One of the things to pay attention to when you are asked these types of problems is to understand what it is that they're asking for, so you know which of the three formulas to be using. So pay close attention to the wording of the problem to see if they're asking for heat capacity, molar heat capacity, or specific heat. Or alternatively, if they're giving you one of those three values in the problem. So if, for example, they're giving you a specific heat value in the problem, then most likely you're going to be using the formula on the bottom to solve that problem. So you need to pay attention to the wording of the problem and what types of values you're given. So for molar heat capacity, the heat is equal to the molar heat capacity times moles of the substance times change in temperature. Again, that comes from the definition of what we mean by molar heat capacity. If you did this by units, you could see how it works out. Lastly, specific heat is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So notice the difference between molar heat capacity and specific heat is molar heat capacity is talking about a mole of a substance, and specific heat is talking about a gram of that substance. So again, the formula here is specific heat times mass of the substance times the change in temperature. So you should be able to work with all three of these formulas in different types of problems. Here's a table of just some specific heats. You would be given these values, so I'm not asking that you know any of these values, but notice the types of units that they're in. So specific heat is joules per gram degree Celsius, because that's what it's defined as, right? It's the amount of heat required to raise a gram of substance 1 degree Celsius. So that's where those units come from. Likewise with molar heat capacity, those units are joules per mole degree Celsius, again because the definition of molar heat capacity is the amount of heat, that's measured in joules, per mole to raise it 1 degree Celsius. So that's where those units come from. So here's the type of problem that you might see for these reactions. Assuming a can of soda has the same specific heat as water, again I would give you that specific heat. Calculate the amount of heat in kilojoules transferred in one can, about 350 grams, is cooled from 25 degrees Celsius to 3 degrees Celsius. Another thing to pay attention to here is to make sure that your units for temperature match your units given in this example, specific heat. So oftentimes you may need to convert from Kelvin to Celsius. So just make sure you're paying attention to that. Another thing that sometimes trips students up is how to figure out the delta T here. Again, delta T is going to be the final temperature minus the initial temperature. So you're looking for the information that tells you that. It says it's cooled from 25 degrees Celsius, so that gives you the initial temperature, to 3 degrees Celsius. That would be the final temperature. In fact, I think they did this one wrong. Not I'm looking at it. So again, we're going to use the equation for the formula here for specific heat, which is Q equals specific heat times mass of the substance times delta T. And they did do this incorrectly. That temperature change should be 3 minus 25, not as it's written there. So, but setting this up, so the specific heat is 4.18 joules per gram degree Celsius. The mass they give you is 350 grams, and the temperature change would be 3 minus 25. And I'm not sure if that's an absolute value or not on that change in temperature. I'm going to check on that and get back to you. I'm used to these being in Kelvin, in which case that doesn't happen. Let's see. I don't see a quick example of that. So again, I'll get back to you on this one. But in terms of setting it up, you're just putting in the specific heat, the mass, and the change in temperature, and calculating that heat evolved. And they did ask for the problem, they did ask for it in kilojoules, so you want to make sure you convert the joules to kilojoules. You can see the conversion factor there, that 1 kilojoule is equivalent to 1,000 joules, so that helps you convert from one to the other. Another concept here is something referred to as the thermodynamic standard state. This is defined as the most stable form of a substance at 1 atmosphere of pressure, a specified temperature, usually it's 25 degrees Celsius, and 1 molar concentration for all the substances in the solution. And we define this just so that we're able to compare back and forth. If they're all at a standard state, you can look at different types of reactions and get information that way. Oh, and I should say that the standard state, if any of your values are measured at the standard state, then you'll see that little degree symbol as a superscript. So on the bottom, where you see the C3H8 gas plus 5O2 gas, giving 3 CO2 gas and 4 H2O gas, is giving you the standard enthalpy change, and that minus 2,044 kilojoules. So you see the little degree symbol after the H there on the bottom. That indicates that you're doing that at a standard state. A couple more definitions just of what we mean by different types of enthalpies, and then we'll use these in some problems. Enthalpy of fusion is defined as the amount of heat that is needed to melt the substance, so without changing its temperature. So just keeping it at the melting temperature. What is the amount of heat that's needed to essentially take it from a solid to a liquid? Enthalpy of vaporization is the heat required to vaporize a substance. So that's, again, that would be taking it from a liquid to a gas, that phase change. Enthalpy of sublimation is the amount of heat required to convert a substance from a solid to a vapor without passing through a liquid state, so directly from solid to gas. And you can see these represented here just in terms of their amounts. One thing to note, and will help you in the problems, is that the delta H of sublimation is equal to the sum of the delta H of fusion plus the delta H of vaporization for any compound. So if you're given, say, 2 of these, you can figure out the third one just by that relationship. A few more concepts here, and that's the difference between what we know of as exothermic and endothermic. The reactions here are shown, and after them you see the enthalpy standard change in enthalpy for each of them. And notice that the one on the top says minus 852 kilojoules, and the one on the bottom says plus 80.3 kilojoules. And so the definition of these exothermic and endothermic reflects those values. So an exothermic reaction is one where heat flows from the system to the surroundings. Another way to think about this is that the heat is given off by the reaction. That's one way to word that. It also can be said that the heat is released by the reaction. That's another way of saying that. All of which are represented by the fact that delta H has a negative sign on it. So because it's negative 852 kilojoules, we can say all of those things about that reaction. The one on the bottom reflects an endothermic reaction. So this is where heat flows from the surroundings to the system. Another way to say that is that the energy is absorbed by the reaction, or the energy is required by the reaction for it to occur, either one of those. And again, that's reflected by the fact that the sign on delta H is positive. Another point here is that if we reverse any reaction, the sign on delta H changes. This will come into play in one of the problems we do involving Hess's law. So in the direction shown at the top, it's an exothermic reaction. If, however, we reverse the direction of that reaction, it now becomes an endothermic reaction. Notice that the value of the heat remains the same because the reaction is the same. We're just talking about it in the forward or reverse directions accordingly. So when we get to Hess's law, you'll see how this comes into play, and that is if you needed to, say, reverse a reaction, you change the sign on your delta H. So here it is. Hess's law says that we can calculate an overall enthalpy change for a reaction by summing the enthalpy changes for individual steps of the reaction. You actually used this when we did the Haber process before. I can't remember what chapter that is off the top of my head, but we used this idea and this law in order to calculate the net energy of the reaction. So we're doing the same thing here. So what they're showing you is the net reaction on the top, 3H2 plus N2, giving 2NH3. And they give you 2 reactions here that you can sum up to get the net. And so you need to just figure out, well, they're asking you for the delta H of reaction 1. Typically you're asked for the net of the reaction, but you could do the same thing here. They give you the net, the delta H for the net reaction, and they give you the delta H for one of the reactions. So you're just looking for what's the one that's missing. So, what added to minus 187.6 gives you that negative 92.2 on the bottom. And this is just showing the overall reactions here. Let me just back up for a minute. Typically, Hess's law, and I think probably the problems you have on homework and your pre-class assignments, will give you a series of reactions, not with delta H values for each. So they'll give you a set of, say, 3 reactions and give you delta H values. And then they'll give you what the net reaction you're looking for is, and they'll ask you to calculate the amount of heat that you get from that reaction. So, and a good example, there's a worked example 8.6 in your text on page 291. So they give you an overall reaction, methane, burning and oxygen, and then they give you 3 separate reactions, and they give you the delta H's of each. And they ask you to calculate the delta H for the net reaction. So what you need to do, this is really a trial and error thing. There are 2 basic things you can do with these reactions, the individual reactions. One is you can reverse the order of any reaction. And again, if you do that, you change the sign on delta H. The other thing that you can do is you can multiply through any reaction by a whole number, so 2 or 3, to get the numbers of molecules that you need, numbers of compounds that you need. And whatever it is that you do to the reaction, you do the same thing to the delta H. So for example, if you need to multiply through by 2, then you would multiply the delta H of that reaction by 2. And then when you get all done and you have set up all your reactions so that you can sum them and the net reaction gives you what you want, then you just add up all of those respective delta H values. And again, I refer you to page 291. I'm sorry, I don't have a slide for that, to see how that's set up. And it gives you an example of having to reverse one and then multiplying one by 2 so you can see. So you can kind of see that at work. And again, it really is a trial and error. You just have to, it's like a jigsaw puzzle. You just have to work around some of those, add them up, see if stuff cancels on the left and the right and leaves you the net reaction. And that's what I should have said that by now, that anything that does appear on the left and the right in all of your reactions cancels out. As you see here, the N2H4 gas cancels on the left and the right to give you the net reaction. So you would do the same type of process for other types of problems that you were given. So this is one way to calculate the delta H of a reaction using Hess's law. We're going to talk about, I think, 2 other ways to also calculate enthalpy changes. So the next way to calculate enthalpy change is to use what are known as standard heats of formation. And the heat of formation is the amount of change required, enthalpy change for the formation of 1 mole of a substance in its standard state from its elements in their standard states. We won't get into too much here other than we're going to use these heats of formation to calculate heats of reaction. So I'll show you how that works. And you'd be given these heats of formation, but here's a table of those values. So here's how that works. If you're looking for the delta H of a reaction and you're given heats of formation for all of your substances, you take the sum of the delta H of formations of all of your products, and that is also, you also take into account the number of moles of each of them that you have as well. And then you subtract the sum of the delta H of formation for all of your reactants. So written below here is just a generic form. So the small letters are to indicate the coefficients in front of any of your reactants or products, and then the capital letters are the reactants and products. So in the larger equation at the bottom, you can calculate the heat of formation here. So I'll do the product parentheses first. So the products would be, and the products are listed first here because it's products minus reactants. So the products would be the number of moles of product C multiplied by the heat of formation for C, plus the number of moles of product D multiplied by the heat of formation for product D. And so that's all inside that bracket. And then subtract from that what's in the second bracket, which is the number of moles of reactant A times the heat of formation of reactant A, plus the number of moles of reactant B times the heat of formation for reactant B. So here's a problem that uses that approach. So using standard heats of formation, calculate the standard enthalpy of reaction for the photosynthesis of glucose and oxygen from carbon dioxide in liquid water. So the reaction is written. As always, you want to make sure that that equation is balanced. And so we're going to use heats of formation to do this. And what you see on the second line is essentially just sort of setting this up. I'm going to focus on the third line because that actually puts the numbers in. So the heat of formation of glucose is minus 1273.3 kilojoules per mole. In our balanced equation, we have 1 mole of that. So you can see that that's in the first parentheses. So that's our product. I'll come back to the oxygen in a minute. Minus 6 moles of our carbon dioxide, and the heat of formation there is the minus 393.5. Plus, we have 6 moles of liquid water, and that's the minus 285.8. I should have mentioned that any compound that you have that's already in its elemental state, so that means those molecules that exist in their gaseous state as diatomic molecules, of which oxygen is an example, their heats of formation are 0. So they're not included. So likewise, if you have other things already in their elemental state, their heat of formation is 0, because they're not actually a compound that's being made, they're existing in that state. So they're not essentially formed, so their heat of formation is equivalent to 0. And again, in terms of the calculations here, again, you always want to do what's inside the parentheses first. So you take that 1 times minus 1273, so you've got minus 1273, and then 6 times minus 393.5 plus 6 times minus 285.8, whatever that is. And then you're going to take the minus 1273.3 and subtract that sum that you've got for the next part. And hopefully that works out to 2,802.5 kilojoules. Another common error that students make in these calculations are forgetting signs. So make sure you pay close attention to negative signs and make sure, just always double check your calculations. So what I would suggest is making sure you write everything out as you see here. Going back to check and make sure that the signs that you have are correct, that the values are correct. And then always do the calculation in your calculator a few times with these to make sure you're always getting the same answer. And that's the best way to just make sure you don't make a silly mistake by missing a sign, is to just do them repetitively and make sure that you get the same answer each time. This next couple slides go through why this calculation works. I'm actually going to skip this. It's showing you the application essentially of Hess's law to this, but I'm going to skip through that. Okay. A third way that we can calculate enthalpy changes is using what are known of as bond dissociation energies. These are different from heats of formation. They're essentially the reverse. So they're the amount of energy that you need to supply to break a bond in a molecule in the gaseous state, and thus the amount of energy that's released when the bond forms. Or they're standard enthalpy changes for you have corresponding bond breaking reactions occurring. So here's a table of bond dissociation energies, and again, you would be given these values, just have to know how to apply them. So here's an example of how you calculate these. So you're given the formula above, hydrogen gas and chlorine gas forming 2 hydrochloric acid, 2 moles of hydrochloric acid gas. And the way that you set these up is that the delta H of the reaction is equal to the sum of the bond dissociation energies for all of the reactant bonds minus the sum of the bond dissociation energies for the product bonds. And yes, again, you need to make sure that you multiply through by any coefficients that you have in your balanced chemical equation. So that applies to this type of calculation as well. So what you see here, the reactant bonds, we have hydrogen and chlorine. So we have 1 mole of hydrogen, 436 kilojoules per mole, and 1 mole of chlorine at 243 kilojoules per mole. And so those are our reactant bonds, and then we subtract off the product bonds that are forming. And so there we have the 2 moles of hydrochloric acid, or the HCl bond. Just a little bit more about that when you're reading these. You can see on this table you have to look at the specific type of bond that you're looking at. So, for example, we've got an HH bond and a Cl-Cl bond. So the HH bond is here with that 436 kilojoules per mole. What was the other one? The Cl-Cl bond is here at 243 kilojoules per mole. So that's where we get these values from. Just in terms of reading, you need to be able to read this off the table. And then HCl is right here. So 432 kilojoules per mole for the HCl. Notice at the bottom that it's possible for you to dissociate multiple bonds, so pay attention to that if you happen to have those in the compounds that you're dealing with. Make sure you're just reading the correct one. And again, as I said before, just make sure that you run these through your calculator a few times just to make sure you haven't missed a sign or made just a calculation error. Let's skip that. Okay, we'll skip that. Okay, the last, I think essentially the last sort of section here is on a little bit about entropy, and we'll talk about free energy as well. I won't spend a large amount of time on entropy, but I will apply it to the reactions that you will look at. So some definitions here. So a thermochemical spontaneous process is one that once started proceeds on its own. A very key part here is that a spontaneous process does not mean an instantaneous process. So spontaneous does not imply time at all. It just implies that a reaction will proceed on its own. And so it doesn't indicate how fast or slow it will proceed, just that it will proceed on its own, that it will occur. Entropy is defined as the amount of randomness in a system, and I'll show you in terms of how we apply that to reactions. Spontaneous processes in general are favored by a negative delta H and a positive delta S value. So I don't know if you've heard that term, that we're always wanting to go to a state of more disorder. That's that positive delta S. Non-spontaneous processes are favored by a positive delta H and a negative delta S. In terms of applications to reactions, the different phases have increasing levels of entropy. So there's less randomness in a solid, so that's at the lower end of an entropy scale, if you will. Liquids have higher randomness, higher entropy than solids, and likewise gases have higher randomness than liquids. So if you were looking at a reaction and asked which would have higher energy, you can look at just the phases to see. So if you were looking at an example where you had, say, two different reactions and you were asked which one would have the higher entropy, look and see what the phases are. If everything in one of them is in gaseous phase and the other one you're looking at is all liquid phase, then obviously the gaseous phase reactions will have higher entropy. You can also consider molar amounts. So if say the only difference between the reactions is that you have 6 moles of gas in one and 4 moles of gas in the other, then 6 moles of gas is a higher amount of entropy than 4 moles of gas. You have more particles that are in, and that will give you more randomness. The last equation here is the relationship between what we know of as Gibbs free energy, enthalpy, and entropy. So this is definitely an equation to write on your exam sheet and know how to work with. Delta G is defined as the change in free energy. So again, delta meaning change in. And delta H we've talked about is the enthalpy of reaction, temperature, and entropy. One thing to point out here, it's very important that when you're doing these types of calculations, you need to make sure that your temperature is in Kelvin, not Celsius. So if it's presented in Celsius, you want to make sure you convert that to Kelvin first. An application of this is when you figure out an answer for Gibbs free energy change, you can look at the sign on delta G to answer questions as to whether that reaction is spontaneous or not. If delta G has a negative sign, then that process or reaction is spontaneous. If delta G is 0, the process is at equilibrium. If the delta G is a positive value, then that process or reaction is non-spontaneous. Okay, and we'll stop there.